learning, maybe the difference between introduction to machine learning concepts in this module. My name is Christian Contino. I'm from the Desktop Build Group here in Sydney, Australia. So what we'll be covering is understanding what is machine learning, maybe the difference between supervised and unsupervised learning, and really this sort of boils down to the need for clean data and how we can use some of the tools on the terminal to help us achieve that. Then we'll quickly cover some of the packages that are available on the BQuant platform, a little bit of disclaimers, and then we'll actually go into an actual example looking at regression, and then a brief conclusion. So starting off, what is machine learning? It's a word that we hear used quite often in not only in finance but in quite a lot of different fields. But really, it gives computers the ability to automatically learn and improve from experience without being explicitly programmed. So really, we're letting the data do most of the talking, and we're trying to extract patterns which might not be immediately obvious to a human, or even sometimes they might be obvious, but the sort of scale of the problem is so large that a human on its own cannot accomplish that. So we've got a bit of fun examples here. This is sort of a classification problem, and really that's more or less what machine learning boils down to. I mean, for us, it's pretty clear that we can distinguish between a person dressed as a traffic cone and a real traffic cone. But if this was, for example, a self-driving car, I think it'd be pretty imperative that the car would be able to distinguish between the two. Not that you'd like to run over either of those, but trying to understand, okay, is this actually a cone that's really close, hence it's really large, or is actually this is a person, so I'm expecting it to move, and anything else that you sort of coded into. So for us, it's sort of a trivial exercise in distinguishing those two, but for a computer, it might not be. So in terms of the broad categories that we have available, in terms of problem sets, I guess they sort of come down to sort of supervised and unsupervised learning, and sort of give you a quick example to make it a little bit clearer. So with the supervised learning, we really need labels for the data. We need to know what the data is, and attach another piece of metadata, which is the label. Is this a picture of a car? Is this a picture of a dog? And let the computer be able to sort of train on this data together with the label. It really does rely on many samples. It has to be clean and accurate data. You can't have things that are mislabeled for one reason or another. And but in the same way, it's very easy to check the performance or accuracy of your model. We can quickly check. Okay, I fed you a picture of a dog. Did you interpret it as a car? Yes or no? Very simple to understand it. On the other hand, we have sort of unsupervised learning, which it comes down to letting the computer do the classification for you and try to extract patterns which might not be immediately obvious. In this case, no labels are actually necessary. We just need to feed it the raw data. But contrary to the supervised learning, it's a bit harder to know, is the actual answer correct? Are we grouping this in a way that's coherent, that actually makes sense? And we've got this example here with these cartoon characters, and we've told the machine, okay, well, go and group them, and it's put them into these three different categories. I mean, by just looking at them, it seems that it's put ducks in one, the mouse in one, and the rabbit in the other. But maybe another way to do it would be, okay, well, let's look at the color of the shoes, or maybe some other feature that might not be immediately obvious. Right. So this is really an unsupervised learning type of problem. So we've sort of all seen examples like this. So this is an example from Google when you try to verify yourself, and really it's actually an exercise in getting clean data. The world is a messy place. The data sometimes isn't as clean as we'd like to have in in toy examples. And actually the role of a quant or any real data scientist is really spend most of the time of cleaning and aligning data. Just by its very nature, you might be getting data from different sources which might label things in slightly different ways. So actually a lot of the time is spent crunching this data to make it sure that it can be fed into a model in a coherent way. So, what we actually have on the right is a way to sort of get humans to click on, say, pictures of road signs. So in this case, you might be clicking on that road sign, and that's all you're doing is actually teaching this as a computer vision problem, teaching the computer, say, this is a road sign. So increasing the number of samples that Google has available for that. We sometimes call this data wrangling. So it's that process of getting data from one raw format to another. And the purpose of it is to sort of add value, make it more valuable so that we can put it into machine learning or any other type of model. So the theory goes a little bit like this. Won't go for each of blocks individually, but it's about taking that data, transforming in such a way that it is useful to you. So in sort of a financial example might be, you've got a portfolio of stocks, you've got some time series, but because you might be looking at stocks across different jurisdictions or different countries, they might have different holidays. So how do you deal with those gaps in say prices? Do you say, okay, well, I might just fill it with the previous day's price? Or you say, okay, I only want observations or days in which every stock has a price. So you might be missing out on a little bit of data there. And these are design choices which has to be made. And this is actually that role of that data scientist, is making decisions in how should we actually be dealing with missing data, spikes in data, or data that you might think does not belong here, or even though it might be not so clean. So what we can actually use to help us along this journey is some of the APIs that we have on the terminal. So some of you might be familiar with some of the BDP and BDH formulas, and so this is really a way to download raw data from Bloomberg servers. This has been around for a long time, and it has served the community very well. But we've sort of moved to a more modern approach, which is BQL, the Bloomberg Query Language. So what this allows us to do is operations on the data server side, which allows to either clean the data, so dealing with those missing data points, or even data transformations, which would typically require multiple steps to be done locally. So at the bottom there, you've got sort of a simple example of saying, I want to get the Z-score of the day-to-day returns for some securities. So in this case, what we'd have to do on the left-hand side is actually, first step is actually download the constituents of the S&P 500, then download the price series, and then do some sort of VLOOKUP or index match to align them up, and use Excel to help us do the first of all the converting prices into returns, and then from there turning those returns into a Z-score. On the right, we've got the BQL example. That's one line. That's all you sort of need to tell it. Say, give me the members of this index and have a set of transformations. So building from the middle outwards, we're saying take the price, turn that into a difference, and then Z-score it for this date range, and that's it. So most of the grunt work is sort of done for you, and that's really the start of the modeling part. Is once that data is actually handed back to me, and now I can actually put this into my regression model or anything else that I'm actually using it for. So really, when it comes down to sort of machine learning in finance, it really deals with trying to work with sort of natural sort of human generated classifications. By this I mean things like credit ratings. Credit rating is obviously generated by humans, by by sort of different models, but even things like sectors or things like country. I mean, country is a little bit more natural. It's obviously very obvious where a stock sits. But what we might want to find is actually maybe hidden classifications. So those ones above obviously are very clear. It's very obvious. We don't really need to know, oh, which country does this stock belong in. It's obvious, right? But what we might want to know is, okay, looking at this sort of time series, is this stock in its low or high vol environment or state? And the same for the economy as a whole. Are we sort of in a recession or expansionary phase? So this is the type of problems that we might want to tackle. In terms of packages used, BQuant has pretty much most of the packages available in Anaconda. The things that would be handy for us, obviously Pandas is the real bread and butter in terms of data manipulation. A few of these other ones are good, and they're sort of a little bit more focused. Things like NumPy, just to sort of do some of the more matrix or scalar multiplication. SciPy and scikit-learn has got some really good inbuilt packages for regression and sort of simple analysis. In terms of plotting, we've got BQviz and BQplot within BQuant. They do work very well, and with just sort of one or two lines, you can get up and running and get some really nice interactive charts. But if you want to use Matplotlib, that is also available to you. My one caveat is things like TensorFlow and Keras, which are slightly more, I'd say, specialized or sophisticated packages. They're not really relevant to the current desktop BQuant offering. This is something probably looking at next year in terms of having more of a BQuant server, and that's probably a little bit more of an enterprise type of workload, just because of the data requirements is obviously a lot larger, much more than a desktop license can accommodate. But we'll revisit that once we have something to show you. So a couple of disclaimers. This is a desktop API, and it is for desktop use only. That really means that you are still constrained by the daily and monthly API limits. There is no free lunch. Unfortunately, using data in BQuant is the same as sort of using data within Excel, so it does count towards your download limits. You can have a look at DaffyGo in terms of getting a little bit more information. I guess BQL does help you in this case. It is your one free lunch because it allows you to do that sort of data compression server side, and only really what gets delivered back to you becomes your consumption. At the same time, BQuant is it's not a reporting environment. Is not there to sort of create PDFs for distribution. At the same time, data can't really leave the desktop and the firm, and just get in touch with your Bloomberg rep if you need to tackle those sort of workflows. Cool. So we'll just be tackling simpler things in this course, in this webinar, that are doable with the current data sets. Look, BQuant is a constantly evolving platform. There'll be more and more functionality available over the coming months and years. So this is not its sort of final state. So let's get to it. So first thing we'll really look at in this webinar series is let's look at something like linear regression. And this is pretty important sort of foundational stage, because it's used by a lot of people, and the outputs are very easy to interpret. There's not really much interpretation required. The outputs are pretty clear. There's a lot of packages out there that do it. Even Excel can sort of do sort of linear regression, and this might be a little bit more of its downfall, but we'll cover that in sort of the conclusion. Cool. So what we're going to look at is trying to understand what is the linear relationship between various data points, right? So maybe we can use that to make a set of make some predictions based on a set of assumptions. What we'll be looking at here is the VIX index price. So this is the actual raw price of the VIX, and I'm just going to be using the S&P 500, and just to make it a little bit more exciting, I'm going to look at the ASX 200 in terms of their return data. OLS, ordinarily released squares, it is fast, it is very simple to use, and we can do it in just a couple of lines in BQuant. I'll show you how the BQL query is formed, how do we actually retrieve that data, and then how do we actually do the actual regression with some of the packages involved. So in terms of the model itself, this is the, if you actually write out, so this is what we were interested in. So it's actually simpler than it looks. So we're saying we want to predict the relationship is that the level of the VIX is dependent on a constant plus some sort of coefficient and the price of the return of the S&P, the return of the ASX, but also we're going to incorporate the return squared of the S&P and also the return squared of the ASX. So the way we can interpret this is a 1 unit change in our predictor variable, holding everything else constant, will change the VIX by one of these beta units. So let's say if the SPX goes up by 1%, it's going to make the VIX go up by beta 1 amounts. You have to really be careful with, say, units and sort of data transformation rather than looking at the price series of the S&P or the price series of the ASX. We have to be really looking at returns. In terms of the VIX, I've decided to go with the absolute level of the VIX rather than the change in the VIX. That's probably, for me, a little bit more interesting, and we can sort of debate outside of this environment whether the VIX level is stationary or not, and at which point does it become stationary. But we can talk about that another time. And we also look at some of the outputs from the regression, and are some of these coefficients sort of statistically significant, and how good is the overall fit. So actually, let's actually get to the actual regression. So I'm going to just open up BQuant here. So this is the BQuant environment for some of you that haven't seen this before, and it's essentially just a Jupyter notebook. Flavor of Jupyter notebook that's sort of been reskinned and adapted to work within the BQuant within the Bloomberg terminal. Just going to zoom in a touch just to make that text a little bit bigger. So these are the packages I'm going to be importing. So obviously BQL, that lets me actually access the data. Stats model, I'm just using this to actually do the regression. Pandas lets me manipulate data frames. So data frames are sort of similar to Excel, where you have a bunch of rows and columns, and it just makes manipulating that data really simple. BQViz, one of our simplest visualization packages, one-liner, makes it nice and easy. Great. So we're just going to start off by connecting to the BQL service, and that lets us access the BQL data items and function. Fantastic, cool. So as I mentioned before, we need to, the pieces of data that we need to download are the return series for the S&P and the ASX 200 and the actual price level of the VIX. I actually need to do this in two sort of separate queries because I'm asking for separate things. I guess I could have done it in one query, so having all of those as my universe, and then asked for the returns and the price, and done some sort of data wrangling locally. But I thought it would be a little bit cleaner just to sort of do two separate queries. Fantastic, cool. So here I'm just building my request for the returns, and you can sort of see how that's sort of built. I'm just saying, give me the return series data item, and my calculation interval is going to be over the past 10 years until today with a daily frequency, and exactly the same thing for the prices, right? So here I'm just asking for prices, which obviously PX last. Anyone that's used any Bloomberg API would be familiar with that. Fantastic. So once I've built these requests, I'm going to use this bq.execute to actually send them server side so that they get delivered back to me into this response. And then I'm going to unpack this response and pivot it so it's the right sort of shape for me. So this is what the data comes back as. response.prices. So even if I look at these sort of returns, this is sort of what they look like, and we have the ID of the ticker that I'm interested in, the date that that price is associated with, and the actual return series. And these are actually stacked on one on top of the other, so I actually need to pivot them so they're actually side by side with dates along the left hand side. And this is what we're doing on this line. We're just saying I want to pivot it. My index is going to be a date, my values are going to be the returns column, and my columns are going to be the IDs, so it's nice and clean. If I just sort of look, what that looks like is something like this. So it's nice and aligned by date. We still have that issue of a NaN, so NaN's not a number. So these are days where there was no data or information. So it could have been a weekend, it could have been a public holiday on that day. So here is our design choice. What do we do with these NaNs? We could just fill them with zeros, but I think from a design perspective, I would rather delete them and have everything really aligned with one another. So what I'm going to be doing here is actually concatenating the data, so which just means it's just joining it into something called data, and then I'm going to be using the drop in a command so that my data is nice and clean. And this is my output. It's a time series of the ASX, the S&P 500 and the VIX, and you can sort of see by the numbers, the VIX is at the price level and the ASX and S&P 500 at the return level. Fantastic. So once we're at this point, we've got the data, it's ready to go, but we need to specify the sort of function that will represent our model. So here we're going to be using stats model. The package lets us sort of specify this in just a couple of lines of code. And from here, we let it sort of fit the OLS model. So in this line here, I'm just going to turn on line numbers to make life a little bit easier. So on line 1, I'm just going to specify what is on the X. So what's on the right-hand side of the equal sign, and on the Y, I'm just going to say what is on the left, which is obviously the level of the VIX. I'm also going to be adding a couple of transformations here, which is the S&P squared and the ASX return squared. The reason why I'm sort of doing this is because I think there might not be sort of a linear relationship between how the returns of the S&P and the VIX move. So maybe once the S&P returns start to get really big or actually really small, so that daily shock, I think they're actually going to be moving the S&P larger than they sort of would when the sort of returns are not being shot. So we sort of have sort of two transition periods. We have a simpler, a low volatility maybe environment, and maybe a high volatility, which is represented by this sort of squared return. Fantastic. So here in this this cell here, this is actually where I'm just going to be adding a constant. So that's just going to be my alpha. That's sort of the base level, I guess, of the VIX if everything else was 0. So where does the VIX naturally sit? And this is it. We just have this on line 2, one line. So stats model, OLS, what is the Y variable, what is the X variable, and dot fit. And that's pretty much it. We're just going to be just run that. We can actually just do a sort of prediction as well. So feeding the data back into itself, and then we actually can get the model summary. So this is the output of the model. So overwhelming amount of information. I'm well aware of that. So the things we really are interested in is this column here, coef. So that's the coefficient that actually tells us the values of those betas. So these are the coefficients, these alphas and betas, and we can interpret them here. So what it's actually saying here is sort of the constant level of the VIX is sort of sitting around 16, and the SPX has a negative value, and actually the ASX has a positive value. But there's also something else to sort of consider is you can have a look at this T-stat or this p-value. Maybe p-value is something that people are a little bit more interested in. So essentially we can if this is oversimplification, we can ignore that value. We're saying this is not statistically significant if that p-value is, say, over around maybe 5%. So in this case, we can see the constant is essentially 0.00. Same for the SPX, but for the ASX 200, we've got a p-value of sort of 92%. So this is saying, well, this has no real statistical relationship between the ASX and the VIX, and that's really the point why I included it there. This is data that maybe shouldn't be in the model, and we could sort of rerun this without it, and it might fit a little bit better. But maybe always be conscious of what you're actually inputting it. If it's just garbage, just try and make it fit a little bit better, or is there some sort of economic meaning behind it? And looking at this, there is no economic meaning. Why should the ASX be affecting the VIX? So, and that's really reflected in this p-value, saying, well, you should be ignoring this. So this is pretty much the output from the model summary, and what we can actually do is plot it. Plot the prediction, so plot the fitted value. So all we're going to be doing is taking that prediction, putting it into a data frame, just renaming it so it looks a little bit better, and then also concatenating that Y value, which is actually the price of the VIX. And this is sort of what it looks like. I mean, we ran it over sort of a 10-year period, so it's a little bit hard to sort of see, but what we can do is maybe look into certain areas. Let's go maybe a little bit more recent, where we've got a little bit some interesting activity. So this is the past year or so. So in blue, we've got the level of the VIX, and we've got those fitted values, and they do an okay job. We could have probably spent a little bit more time thinking what variables are actually important in this, and maybe excluding the ASX, which clearly from the results above is telling us it really shouldn't be there. Fantastic. So let's just go back to those slides. Cool. So I'm just going to conclude it here. So just summarizing it, we've used this linear framework, this OLS model, to visualize what is the relationship between sort of two variables. It is a convenient tool. It might also be its curse. So to someone with a hammer, everything looks like a nail. So people tend to just use and abuse OLS because it is so simple, because it's so approachable, and the values are easy to sort of interpret. But it really only works in a certain environment, and that is we're trying to model linear data. We can do some transformation to the data, like we've done here. We've squared some of the returns to try and sort of accommodate some of the non-linear nature of it, but there are better tools sort of for this. If you torture the data and try to make it reach your sort of foregone conclusion, some people call this sort of p-hacking, and it's really trying to put in data that maybe doesn't belong there, transforming in a dubious way, just so that the model, the end result says, yes, this is I can explain this relationship based on this. I mean, it really makes the whole thing pointless. If you already have your answer, and you're just sort of trying to backfill what the model should be in order to sort of reaffirm what you want to achieve, it makes the whole process a little bit pointless. Cool. In the topics, in the next few webinar series, we will look at things a little bit more complex, things like non-linear relationships, but also things like clustering and dimensionality reduction, which come in really handy when we have quite a large amount of data and we want to explore relationships which are not immediately clear. So we'll cover those in the next couple of webinars, and please keep an eye out for those. Thank you. Hope you found this webinar handy. If you want to know more about BQuant, you want to chat to any of us, please reach out to any of your reps, and we'd be more than happy to arrange a call and really know what sort of projects you're working on, and try and help you with those. Cheers. Thanks. Bye.